Hi everyone, we're back at the Hack Summit, and we're joined here by Grady Booch, who co-created the Unified Modeling Language and also developed the Booch method as presented in his book, Object-Oriented Analysis and Design. He's published more than 7 books and articles. He was awarded an ACM Fellowship in 1995, and both the World Technology Network and IBM Fellowships, awarded a BCH Lovelace Medal in 2012. He received a Dr. Jobs Excellence in Programming Award, and is the winner of 3 Jolt Awards, and is a personal hero of mine. It's an honor and a privilege to have you here, Grady. Thanks for joining us today.
Thanks, Ed.
So I'm going to go ahead and mute
So,
myself and my video,
okay.
and I'll be back afterwards for Q&A. So take it away.
All right, very well. You bet. Thanks. So, I'm delighted to be here. Gosh, where to begin? Many of you have no idea who I am. Many of you may have studied the UML in university and absolutely loathed it and never used it again. And I think that's actually wonderful. I use the UML still. I'm not involved in the UML standard at all anymore. And indeed, most of the UML diagrams I create, I throw away because they're really just there to help me reason about things. The most recent thing for which I used the UML was to try to understand and describe and document the architecture of IBM Watson, which was pretty cool. So let me tell you what I'm up to these days, because I'm going to segue into a presentation that is very, very different than the other ones you have seen. There are 3 things that keep me busy. The first of which is I go about the world helping organizations with their architecture. So I've worked from everything from large banks to defense contractors to startup, mostly in the area of how does one take the existing legacy code they have and begin to transform both the architecture as well as the organization itself. That's maybe 10–20% of my time. About 30% of my time I'm involved in IBM's cognitive systems work. Several years ago, I got involved with the IBM Watson project, the Jeopardy challenge, and my task there was to do an archaeological dig upon the 1.2 million line code base that formed Watson and basically describe it using UML, which was quite effective. The thing I've been involved with in the last year and a half has been to lead our research activities as to what we do beyond Watson. Watson's great. We're commercializing it. We just made a $1 billion bet to create a whole new division. But my interest is, what do we do in the next 5 to 10 years? So that's one of the places I'm working in. Another variant of that is in another language area. We have developed an entirely new programming platform in terms of artificial neurons at the density of the human brain. So with about 80-watt power, about the size of a melon, about the size of the human brain, we can pack 10 to the 15th to 10 to the 16th artificial neurons. And the interesting question is, how do we program this thing? Because it's a non-von Neumann machine. So that's another one of the activities I'm involved with. The third thing, which is what I want to talk with you today about, is my passion. Is a project that's a little different than anything else you've seen or heard here today, and that's a documentary that my wife and I have been developing the last several years in conjunction with the Computer History Museum. So we're going to go off on a little bit different tack than on the UML. I'm happy to attend to some of the UML questions, and let me again say I'm delighted for those of you who are using the UML. I fully respect those of you who aren't. Frankly, I think the UML standard has gotten far too complex. I use the UML so largely as a language just to understand and reason about something, and I throw everything else away. I tend to use 20% of the UML, and that's good enough, and that's if all you use, then more power for you. But my interest has been as an insider to technology. How do we attend to what the public does as we slowly surrender ourselves to the things that you and I create? You and I are in a very privileged position because line by line, the things we do are changing the world. And that's a privilege to be able to do what we do. But it's also the case it's a responsibility because we are changing the world. So in this documentary effort, we were very much inspired by what Carl Sagan did in Cosmos. To give you a quick update here, we've been working on this for about 5 years now. Last year, we hooked up with KQED, the PBS station in the Bay Area, and we developed a teaser and a treatment, which we then took to corporate PBS in DC in the spring of last year and pitched it to PBS. They absolutely loved it. So the path we're on now is finding the producer and director for us. We believe we found one in the London area we're working with, and we are basically developing the rest of the series. What you're going to see now is some of the insights that we have and the kinds of messages we're trying to take across to the general public. I'd like you to take a look at computingthehumanexperience.com. You'll find some things about our site there. Follow me on Twitter. I'm Grady_Booch. And of course, in this holiday season, every time I gain a Twitter follower, an angel gets its wings. So please do follow me. But let's now go on a journey here of where this computing in the human experience is leading us. So let me move up to some slides here and share something. Here we go. And let's share. As I said, we're very much influenced by what Carl Sagan has done, and I love one of his phrases in which he said, we live in a society that is exquisitely dependent on science and technology, in which hardly anyone knows anything about science and technology. Let's reframe this and say that we also live in a society that is extremely dependent on computing, and hardly anyone knows anything about it. We look at these screens. I see, babies walking around with them in their strollers, and there is an incuriosity as to what happens behind the screen of that iPad. Alan Newell, one of the real gurus of the beginning of AI, observed once that we live in an enchanted land. And what he meant by that is he saw the future, that we're going to be surrounded by computing devices that will look utterly like magic. The way I like to phrase it in a poetic fashion is that software we write is the invisible thread, and hardware is the loom on which we weave this fabric of computing. And that loom allows us to celebrate what we can be as human. It also magnifies the worst in us. And in many ways, it challenges us what it means to be human, to be sentient. If you think about what physicists have done, they start with the world of immense complexity. And we see the universe, we see how it operates, and they try to build models of simplicity in terms of how this complexity comes to pass. From this, we have things like the Standard Model. And the Standard Model is exquisite in that it shows us in some very simple fashion how it is that the universe springs from these simplest of things. Well, if you think about it, we as computer scientists are doing quite the opposite. Now, even though we understand the world, by the way, even though we can build these kinds of models, it is the case that science is something that progresses in a very careful, logical kind of fashion. We look at the universe, we examine it, we make hypotheses, we test it, we look for available evidence, and we always subject this to correction and improvement. Even though we may look at the sun, a sunset, as Richard Feynman once said, we are not diminished as scientists looking at the beauty, because there comes from that a sense of awe. We can get a sense of curiosity and really a reverence for the natural world. One of my premises is that we as people living in this world can see that as we look at the universe, we as insiders to technology have that same kind of feeling. I can look at a large piece of software and I will experience some sense of awe as to its beauty associated with it. There is indeed inherent beauty inside these things. From a scientific perspective, it leads us to some big questions. How did the universe begin? What's the universe made of? How is life and how did it begin? What's the nature of consciousness? I had an interesting discussion in the green room as we began here. My premise, as you'll see, is that the mind is indeed computable, and in many ways consciousness is an illusion. But we'll come back to that in a moment. But here's my premise, and I wish I could animate this slide, but it comes from a wonderful visualization called Code Swarms. You can see it on Vimeo. And it takes a look in this visualization of the changes in check-in and check-out in the Twitter code base. There really is a lovely beauty to hardware and software that, in my world, is just as elegant and just as awe-inspiring as one might see in the motion of the stars or the pulsing of life in the cell. For somebody in the outside world who is not a part of technology, they don't see that. They see just the screen in front of them. They see the magic. One of my desires, one of my goals is to try to expose that beauty to them. Now, as I said, from physicists, we look at the complexity, the raw complexity of the universe, and we try to distill that into the simplest kinds of things. We do something very different in computing. We start from the simplest things, the basics of the Turing machine, for example, which is the basis of all of computability. And from that, we build astonishingly complex things. For example, there was this wonderful survey somebody did, this graph, in which they plotted out the sizes of code bases for a variety of systems. So you might find a simple iPhone game of just a few thousand lines of code, maybe moving up to the space shuttle where we're talking now, around 400 to 500,000 lines of code. If you keep moving up to the sizes of systems that many of you might have been involved with, Photoshop, for example, roughly around 15 million or so lines of code. By the way, go to the Computer History Museum site and you will find the original source code to Photoshop 1.0. You'll find the original source code to Windows. You'll find the original source code to DOS and a number of other things like that. Great programmers learn by looking at other people's code. Mars Curiosity rover was around 15 million lines of code. Moving on up, we see things like, let's look here, for example, Microsoft Office. We're now on the orders of 40 to 50 million lines of code. And even things like healthcare.gov, which we were just hearing about, this number on this chart is actually a bit wrong. They were looking at all the other pieces associated with it. But nonetheless, we're talking about systems that you and I build that are of astonishing complexity. Now, it is the case that as we move about in the world, and here we have a shot from New York City. If you look closely, you'll see me in the background someplace. We are surrounded by computing. In many ways, we as individuals, we who are not inside computing, those of us who are outside of computing, are slowly, irreversibly, intentionally surrendering ourselves to computing technology. And we're doing so in very, very subtle ways. But it's not just us in this first world. We see it transforming, as you are well aware, in the third world. In the places where there is no computing infrastructure, mobile computing is taking great hold because it is the way that individuals can connect with markets, individuals can connect with one another. It is the place where computing is reaching the ground of non-industrialized kinds of countries. Alan Newell, to go back with him, this is the quote he observed: "Computing technology offers the possibility of incorporating intelligent behavior in all the nooks and crannies of our world." We speak of this in the marketing term of the Internet of Things, and Alan Newell, observed this back in the 60s as this is the direction we were headed. Who could have conceived of doorknobs and thermostats as having their own IP address? But it is certainly the case that's where we are. I wear a Fitbit, and it's connected via Bluetooth to my phones. So we see the future leading us to these kinds of devices where we're pervasively connected. And these are the kinds of things we're creating. Now, just as physics leads us to the questions, the big questions of the world, why are we here? How did life get created? Computing does a similar kind of thing. It asks us, like, what are the limits of computing? Is the universe itself digital? Is the mind computable? And in many ways, what are the consequences of computing for humanity? These are the kinds of questions that I've been spending a lot of time thinking about over the last 5 years. My premise, in many ways, is we live in a society that is so exquisitely dependent on computing, and yet most hardly know anything about computing. You'll hear some stories about this in a moment, but ask to some of your colleagues who are not in the computing world, and ask them if they know how the computer works, or when they send a message on Facebook, how it actually works. And I think you'll find that they are astonishingly, woefully inadequate in their knowledge and understanding of it. So in order to understand our present, I want to go back to the past. So let's look back at the time of Charles Babbage. So here we are in the mid 1800s. Think about this time for a moment. And he was a person who was very much caught between two worlds. He was, first off, a young earth creationist. He was a person who believed what the theologian, the Bishop of Usher, said, that the earth was some 6,000 years old. And yet, we saw tantalizing evidence from people like the geologist William Smith, who was going about the UK at the time, who was discovering that there were some things happening in the studies of road cuts that challenged the thinking about the young Earth. So Babbage was kind of caught between the two. If you were in Babbage's time, you had about, what, 1.26 billion people in the world. There were 23 million people in the U.S., 3 million of which, by the way, were slaves, and 64% of the workforce was in agriculture. Only 1 in 5 people lived in the city, and very, very few people attended school. You would have read. Things like The Scarlet Letter, Moby Dick, David Copperfield, Uncle Tom's Cabin. Those would have been the things somebody would have read. Now, let's consider the movement of information back in this time. In the early 1800s, if you were in New York City, it would take you 6 weeks to get to the edge of the frontier, and it was not necessarily a guaranteed trip by any means. By 1830s, if you were in New York and tried to get to the edge, it might take you about 3 weeks or so. But in the mid 1800s, things transformed because of the presence of railroads. So to get from New York to the West Coast might take you now 4 to 5 weeks is all. Along with the railroads came an unintended consequence, namely the telegraph. So the telegraph came along at first primarily as a communications mechanism to allow the trains to coordinate their tracks, where they are on the tracks, to telegraph ahead when a train was late or when it was going to be on time. But what was happening then is people began to use the telegraph also as a communication mechanism for beyond the railroad itself. So now information was traveling much faster than a human could travel by walking or on horse or even a train itself. That was utterly transformative. If you think back to this time, the second half of the 1800s, Mark Twain viewed this as an extraordinary time in humankind. He wrote a letter to Walt Whitman upon Walt Whitman's birthday, observing, what incredible things you've seen. You saw the steam press, the steamship, the steel ship, the telegraph, the telephone, the photograph. All of these things were transformative. So for people in that time, let me assure you that their world was just as transformative as we are seeing it here. They saw astonishing changes in their lives. And because of the rate of change was so high, the future was not evenly distributed, as the phrase goes, but it was very, very transformative for everyone. Now, let's look at it from another perspective in this movement of information. So if you look at how long it took information to go to, say, London, and this is again in around the 1800s or so, the Battle of Trafalgar took some 2 weeks to go from where the battlefield happened to London itself. There was a tremendous earthquake in India in 1890, and it took several months for that information to get to London. When Lincoln was assassinated in the United States, it took 2 weeks to get to London itself. Well, we're in a different world. I live here in Maui, by the way, and it's a wonderful place to live. And oftentimes we will get tsunami alerts. We live on the Pacific, in the middle of the Pacific, of course, and the Pacific Rim, the Rim of Fire as they call it, is prone to earthquakes. And so when an earthquake happens in South America or in Japan or in the Northwest, then the chances of us having a tsunami are actually very, very high. It is the case that gravity wave, the earthquake waves travel somewhere around 3 to 5 kilometers per second. But fiber waves travel somewhere close to the speed of light, around 200,000 kilometers a second. So what will happen is that the earthquake will happen, and it won't be detected at an earthquake center like in Boulder for several more minutes, because the earthquake waves take a while to travel to the Earth. but you actually get tweets ahead of the physical occurrence. And as this wonderful cartoon showed from XKCD, you'll find that once you get beyond 100 kilometers, the tweets about an earthquake actually go ahead faster than the earthquake itself. So we here in Maui will hear about it ahead of the earthquake actually affecting us in this particular location. So we live in a fascinating world. Our technology has made it possible for us to do things that are in effect faster than natural processes. So what do people do with this kind of thing? I live on the beach. You're actually looking here at a picture next of right outside my front yard. My wife has this wonderful little hobby in which she tries to take pictures of people who are walking along the beach. So you see these wonderful sunsets. It's gorgeous outside. Whales are jumping, the waves are crashing, and so what do you see people doing? Well, you see a guy walking around looking with his head down at his iPhone. You see all the 20-somethings who are staring at their iPhones as well too, and then you see people like this. And of course, my question is, where does she put her phone as she goes into the water? I have no idea. But you know, this is what happens. Technology has utterly changed the way we view the world, and I see it on a daily basis. Is this going to lead us to a dystopian world? Well, Sherry Turkle, worries very much so in her book Alone Together that this is the direction we're going to head. That computing is very much impacting the way our brains are wired. It's impacting how we relate to people. It's impacting social skills among young people. Well, I wish this was actually layered, but let me show you some quotes here, and you could think these were from contemporary times. People have said the art of conversation is dying. We do all these short notes instead of sitting down to have a good talk. And really, what technology is doing for us is destroying our memory. Except that these aren't contemporary things. These are things that were written back in the 1800s and way back into 450 BC. The last one here was actually from a dialogue from, I think, Socrates, in which he was lamenting the creation of the written language, that he thought that having written books was a bad thing because now all of a sudden we wouldn't remember stuff anymore. But clearly we have proven that the written language, the spoken language, the written language technology has many, many good benefits. Well, let me tell you another personal story here. This is one of my godkids. Tara is her name. And I remember having a conversation with her once. We took her on a Disney cruise, of all places. And here's a picture of her with her mom, and we've got Mickey, of course, my wife, on the other side. And we've shown her this picture of late, and she said, "Oh yes, that was such a wonderful time in which you got to meet Mickey," except that it's not real because Tara wasn't feeling well that day. And so the three adults got together with Mickey and we took the picture, and my wife photoshopped Tara in, and yet Tara believed she was there. So we have the technology in many ways that changes our understanding of the past. I have another goddaughter by the name of Molly, and she, in fact, sort of inspired me to do this documentary in some ways. We told her about what we were doing. She said, what do you do? What do you know about computers? And Molly said, well, I know everything. I took a class. Well, what do you learn? Oh, I know how to make a Facebook page and write a Word document. To her, that's what computing was, and that was sufficient. I am happy to see things like code.org, what the Khan Academy has done, all these places that are trying to introduce computing to K through 12. We know that in the Common Core, like it or not, there are a set of standards relative to language arts and literacy and mathematics. That's a good thing. We have also code.org, which is a good thing, and Computing in the Core has been working to develop similar kinds of standards for computing for the computing core itself. And of course, I celebrate all these others: Code Academy, Code School, Treehouse, Google's Made with Code. I think these are all wonderful and good things because just as in the 1800s, I needed to know some basics about agriculture and horses and doing my own, making my own clothes and making my own crops. Similarly, for our current generation, knowing how to code, I believe, is fundamentally an important skill. I'm also delighted by groups such as the CTSA, the Computing Research Association. I addressed them in a keynote earlier this summer. This is the department heads of all the universities in North America. These are the kind of groups who are also concerned about these kinds of problems. Another thing that I think is delightful is the presence of the Raspberry Pi and the Arduino, because in my day growing up, we didn't really have these kinds of devices at our disposal, but now you've got devices that you can, get down to the raw hardware, and I encourage people to, go one down one path or the other to get very, very close to their hardware and teach that. This is actually very similar to what the BBC did back in the late 1800s. There was a documentary called The Mighty Micro, and from that, the UK said, computing is important for us as we move to the personal computer. Let's teach all of UK. And so they developed this long documentary series, created also the BBC Micro with Acorn Computing, and it really taught a whole generation of folks. There is a similar literary program going on now in the UK in which through K through 12 is being taught computing in every school, and this is actually government developed, not just privately so. We have another friend in my family, a niece, and I'm convinced that even the youngest can be inspired by what we do here. As someone said, we're going to teach you to code, and the 5-year-old says, what's that? And the way the aunt put it was, it's a secret language you use to tell computers what to do. That's cool. We don't just want to teach computing as a vocation, we want to teach the really cool things behind it. Lyrically, the way I put it is that software is the invisible writing that whispers the story as a possibility to our hardware. And it's those kind of stories that we want to teach people to do. If you've studied my OOD books, you may remember this cartoon, which I think is still very, very relevant. We are here building systems of enormous complexity, and yet our goals as developers is to make those the simplest things we possibly can be. Excuse me. So let's transition for a moment to what we're trying to do here and the stories we're trying to tell. The question I'd like to ask you is, what do you believe? Yes, you're right. Not the 1800s. The BBC Micro was 1980. Thank you. What do you think are the stories that the general public needs to know? What does somebody who is not inside computing need to know about computing? For me, the answer is this notion of computational thinking. It's an idea that came out of Jeanette Wing from Microsoft at the time, and her view of the world is that computational thinking is not just how to code, but really it's a way of solving problems and designing systems. It's a way of thinking about how to approach a problem. Just as science is not a collection of facts, it's a way of thinking. It's the case that computational thinking is a way of how to approach the world as if it were computable. So it means thinking algorithmically, and that's the kind of thing that needs to be taught. I celebrate the teaching of coding. That's good, but that's the vocation. I want to teach the skills of how I think algorithmically. My wife was talking to our goddaughter once, and she said, in college we had this test where we had to identify 30 rocks, and the 18-year-old said, you don't have to do that, you can just Google it. And my wife observed, we didn't have Google when I was in college. And the 18-year-old girl was just astonished. We have a generation behind us that has grown up not knowing the internet never existed. But in many ways, where we are today is based upon that history. I think if you mention some of the names of the greats in computing history, the average person on the streets would say history sort of began with Steve Jobs, and anything before that was pretty much uninteresting. It was kind of, big machines. Part of what we're trying to teach in this documentary series is not just the implications of computing, but also a little bit of the history, some of the science, certainly, and part of that history shows about how we build upon one another. So this is a picture of me in Second Life. Yes, I still work in Second Life from time to time. But to have gotten us there, we had things before that, things like the modeling of the world, as you see in the Google car itself, which was, we're talking about hard real-time devices. Now, clearly, Second Life was before this, but I'm giving you an instance of the kinds of virtuality we see. Before, what we could see in the air realm of the Google the Google time frame was, of course, the personal computer and the mainframe itself. Before that time was the time of the vacuum tube computer, and before that time, of course, was the time in which computers were human. Indeed, the first computer programmers were probably women. If you look back in the times in which many tables had to be created in the work done at Bletchley Park, most of the computers back then in Bletchley Park were indeed women, not men. So think about the kinds of things we can do with computing. We can, especially with large computers, we can model virtual life. We can look at the large-scale structure of the universe. We can predict weather. We can look at shock waves and thermonuclear events. These are the kinds of things we can do. But I should mention this is exactly what John von Neumann was doing back in the 40s as well. He was doing every one of those things, exploring it on the Johnniac, which was an astonishingly underpowered machine built upon vacuum tubes. So in many ways, the kinds of things we are inspired to model and build haven't changed. We have always had this desire to model the world and build things beyond ourselves. What has changed, of course, is our machines, our software, our ability, and how we build these systems has greatly increased. Now, I mentioned earlier that there are some things that we can and can't do. This is my notion of the limits of software. You look at the average person and they'll say, well, gosh, I can do anything in computing. And my reaction to that is, no, we actually can't. There are some things that constrain us. One of those is the laws of physics. So we know, for example, that information will never travel faster than the speed of light. So that's a limiting factor. We also know that as you start shrinking our integrated circuits down to smaller and smaller levels, if you get down to 7 nanometers, for a chip, that kind of level, quantum effects begin to play a role. We see a way now to put a single bit, a single transistor in about 100 atoms. That's not uncommon. We see a path that will bring us to a single transistor to, a single bit to the level of a spin of a single electron. So that's the level that theoretically we think we can get to. And even then, as Feynman would say, there's plenty of room down at the bottom. So on the one hand, yes, there are limits to physics. The laws of physics limit us, but pragmatically, not necessarily so much. With regards to algorithms, for example, we know that there are limits to the kinds of things we can do. There are clearly some problems that are not computable. There are many problems that are NP complete as well too. So there are some things that may be very simply stated but are impossible to calculate within the lifetime of the universe. These are limiting factors. But what we're finding in our limits is that many times good enough algorithms are good enough to get us closer. So even then, we have this progression in computer science to build better and better algorithms. We know the theoretical limits for many things, but we can still also do many good enough things. It's also the case that we see limits with regards to our abstractions. And this is one of the interesting things as we move to design and architecture. Excuse me. You can see this especially so in the world of computer graphics, because the earliest days, we were able to build things that were very simple 3D or 2D kinds of art. What you're seeing on this picture is actually computer generated of a human, and it's so photorealistic. We know how to build models of humans that really cut across the uncanny valley. And this was very much a combination of being able to develop the right abstractions to be able to develop the right kind of algorithms. This is where architecture comes into play. As you know, my philosophy, all architecture is design, but not all design is architecture, and architecture represents the most significant design decisions. So what you're seeing here is a very simple level of what the Watson architecture is. Watson is a pipe and filter architecture, and I've got well, actually I didn't throw in a diagram. I've got UML diagrams for every aspect of it, and we can document the architecture of Watson, about 1.5 million lines of code, in about 15 UML diagrams, and that's enough to get you a sense of the key design decisions. Now, Watson was a breakthrough in the sense that we now know the basic architecture to build as a system that can answer questions in amazing fashion. And so that architectural breakthrough went a long way. Now we get to the non-technical things. This is where it becomes a little bit hard. When I go in and work with an organization, many times I'll show up as an Uber geek and say, do this and do this technically. On the other times, I'll show up as Dr. Phil and say, you're having problems with your politics or your organization, you need to do this. This is the level of organization. And I urge you to take a look at Jim Copleen's book, The Organizational Processes of Agile Projects. Organizational patterns of agile projects, in which he's identified a few dozen common patterns for how well-structured organizations tend to architect themselves. This is a hard problem. I'm very much a fan of agile methods. Indeed, I would have been one of the signers to the original Agile Manifesto, but I was out working with a customer. So I think these kinds of practices are great, but clearly we have to move up to systems that scale, and this is where the balance between agile and architecture comes to play, which is another hour talk unto itself. Now we begin to move to the level of economics, because this also can impact the kinds of things we can build. This is the notion of where technical debt comes into play, and I see this all the time. We rush out against a deadline, we do some things, we build these kinds of things that have technical debt, and we have to pay back that debt over time, otherwise it's going to kill us. Facebook has a legacy problem, and you've seen this in the transformation that Zuck spoke of in the way that they are changing their development processes. It used to be, move fast and break things. You'll see now they speak of it as move fast but build upon a stable infrastructure. Folks, that's architecture, and that's really what they have come to learn over time. And finally, we get to the human level, because now we are dealing with systems that impact humanity. I'm going to make a statement here that you may or may not agree with, but it's something that I think is very, very true. Every line of code you write has a moral and ethical implication. It has an implication because we are using it, we are developing things that people use that their lives depend upon. And so it may not look like it at the subtlest level of what you're doing, but it builds upon it line by line to build systems that impact society. Let me give you an example of this. The cost of sequencing a genome has radically decreased. It took, in the first genome sequencing that Craig Venter did, it was about a $100 million effort. Sequence one genome. We saw a great decrease in the cost of genomic sequencing around 2008, because now we were able to throw lots of hardware at the problem. And now we're at the point where sequencing an individual genome is about $1,000. We see a path to bring us to about $100 per genomic sequence. There's an effort going on at IBM called the DNA transistor. We have a bit of silicon we prototyped that has a hole in the size of it about the size of a DNA strand. You drop DNA through it, and we basically sequence the DNA as it drops through. There are a number of other groups working on this same thing. Once you get to the point where you can sequence DNA for $100 a genome, then amazing things happen. And ask the question, well, wait a minute, if I can make it cost affordable, should I allow cross-sectional studies across billions of people? Should I allow parents to genetically engineer their children? Let's make it more personal. Suppose your daughter had a child, and that unborn child had a debilitating genetic defect. Would you support them aborting that child? We have the technology in play in this generation to be able to make those kinds of decisions. Here's what the future means to me. As I project out the next multiple years, and this is what I do as a fellow, I worry about the next 5 to 10 years. We are going to live in a world with abundant computational resources, where nothing is forgotten, and we are connected in pervasive, unexpected ways beyond our choice. And that's an important phrase here. There are things we do that connect us that I have absolutely no control over. I leave this digital ephemera wherever I go, based upon the devices I have, based upon where I go in the world. It is utterly inescapable. And that's why you see these fierce debates about privacy versus security. Frankly, I believe that the two are utterly compatible, that I can have privacy with security, and yet what we're seeing happening in our governments is warping the discussion horribly. I'm just absolutely offended by the same things I see governments doing, but that itself is another hour conversation. So given this future, I think it's reasonable to stop and ask ourselves, what kind of world do we want to create? Because you and I are the ones creating that. So here are my assertions, and these are the basic assertions we have for the documentary series. I think that we as a species are irreversibly surrendering ourselves, and we're going to co-evolve with this technology. I believe also it's a technology that leads us to a dichotomy of abundance and destruction. If anything, what we're seeing with computing, it is widening the gap of wealth in many ways. I also observe that privacy is a recent illusion. What I mean by that is if you look through most of human life, we had actually no privacy. There's this great book called Privacy and Solitude in the Middle Ages, in which you'll see that privacy is something that only the wealthiest had, because they had their own rooms, their own bedrooms. Everyone else had basically no privacy whatsoever. I would claim that the kinds of privacy we see now and the way we push back against our attacks upon privacy is a relatively recent phenomenon, and in many ways we as a species are still coming to grips with that. I also have the assertion that the mind is computable, and this is another talk unto itself, but I'm a materialist, but I'm also a spiritualist, and I can reconcile those two views of the world, that I believe that what we have, the notion of consciousness, in many ways is an illusion, and that it's possible for us to compute the mind. There's another premise that I'm toying with, and I'm a little bit on the fence on, as to whether or not the cosmos itself is digital. We have the reality of the Planck length, which appears to be the fundamental limit of size in the universe. We have also Planck time, and we also have the notion that energy levels are discrete, which has some very tantalizing evidence that suggests that the universe itself may be digital. And that has implications that we may be living in a world that's based truly upon information and, truly upon matter and energy, but the fundamentals themselves may be information. Clearly, I believe that computing is a moral activity, and we as developers have a moral responsibility therein. Now, here's the chilling thing that I'd like to leave you with, that no matter what future we envision, it's going to depend upon computing systems that we have not yet created. The future is really pretty awesome. That even though you may say, gosh, we have all these wonderful things, there is a tremendous amount of things yet to be done, and a lot of that's going to happen based upon the computing systems that you and I build and that we make possible for the next generation to build. So let me wrap up here, because I do want to have time to talk about some of the UML stuff as well. This is the documentary we've been working on. Follow me on Twitter, please. You can go to the web here. Stay tuned, because as I said, we pitched this to corporate PBS. We've got a book series with O'Reilly Media. We're actually looking for authors as well too. Could you always use volunteers to help us in this project, but that's the effort that I'll be spending a lot of my time on. Its intent is to teach the essential science. We want to talk about some of these cool stories. We want to look at the connections among computing and science and society. We want to contemplate the future as well. John Pierce, who was one of the people that supervised the folks at Bell Lab who invented the transistor, said, you know, after growing wildly for years, the field of computing appears to be reaching its infancy. This is back in the 50s, by the way, and I think the thing is still absolutely true. Nicholas Negroponte once observed that computing is not about computers anymore. It truly is about living. Don't get me wrong. I think sometimes writing code is better than sex. It's a whole lot of fun, but it's also the case that the things we do is very, very cool and changes the world. And it really is about living. So it raises the questions, I think, that computing helps us answer. Who am I? Why am I here? What comes after me? How can I be at peace? Bill Joy, in his delightful article, The Future Doesn't Need Us, wrote, I'm working to create tools that will enable the construction of the technology to replace our species. Bill was very, very uncomfortable about that. I respect Bill, but I disagree with him. My view of the world is that computing has something to extend us, to transform us. It may even destroy us, but nonetheless, I am absolutely confident in the strength of the human experience and human spirit to absorb and adapt and evolve. That's why I observe that the story of computing is a story of humanity. It's a story that affects all of us. It's a story that you and I are helping to create. And it's really cool to be a part of that story. So let me finish the slides here. We'll open it up to some Q&A, and I saw thousands of questions come across. Thank you, thank you.
Grady,
Ed, back to you.
that was an absolutely epic presentation. I was completely blown away, and the audience was too. I think the quote that they're fixated on right now is the line, "Coding is better than sex." You heard it here for the very first
Yes.
time, Grady Booch.
To a true programmer, this is absolutely true.
This should be an interview question to find out if someone passes the interview to be an employee as a coder. Only the true programmers think this way. And other audience members I'm just looking at the chat. They're just kind of flying in here. It would be awesome to see this aired on TV. You could do for computer science what Cosmos did for physics. That's what people are saying about your presentation.
That's what we're trying to do. Yeah.
Incredible job. I've gone ahead and polled the audience while you've been speaking here. The first question was a UML-related question. Most of the audience members have used UML, so you've made a significant impact for the audience. And then I asked this kind of cute little question, do you believe P equals NP? So let me explain this to the audience for those of you who don't quite know what I'm talking about. In Grady's presentation, he talked about the idea of computability and how certain problems may be NP complete. What that basically means is there's a certain set of problems in computer science that are so difficult to solve that they can only be solved in kind of an exponential amount of time rather than a polynomial amount of time. And this class of problems are special because if you can solve any one of these problems, then the solution for that problem can be used to solve a whole host of other problems. And they're all in the same group of problems called the NP-complete set of problems. And so the question of does P equals NP really is that's a question of are the NP-complete problem sets solvable in polynomial time? So most of the audience did not understand the question. That was their answer. But the second most popular answer was no. Most people do not believe P equals NP. And then the smallest percentage thought, yes, P equals NP. What do you think, Grady? Do you have a personal opinion on this?
I'd say it's not an issue of belief, but certainly where the mathematics leads us to now is that it's an overwhelming no.
Yeah, this is, I believe right now, it's still technically unsolved, right?
It is probably an unsolvable problem, yes.
Mm-hmm.
But tantalizing evidence suggests that it probably is not the same. But even if it is, that it is the case, we still end up with some uncomputable problems. They're computable, but beyond the lifetime of the universe, and therefore pragmatically, they're not especially interesting to me.
Mm-hmm. Yeah, I mean, if you look at kind of like chess, for example, right, as a game, right, there's so many possibilities for how you can move the chess pieces. Theoretically, chess has a solution, right? There's a solution to chess, and the answer is probably white. White is probably the right answer. You should start with white, not black, and make certain moves. Because white gets.
Well, look at a pragmatic one of FedEx. FedEx has, tens of thousands, if not millions, of packages in play at one time. What is the optimal path for a package in FedEx? The answer is it's absolutely an NP problem, NP complete problem, because the N is really, really large, and yet they still make money because they do a good enough solution, good enough algorithms.
You're referring to a traveling salesman problem there, right?
Which is NP complete, right?
Exactly. So they have this approximation algorithm where they distribute the boxes to a central warehouse and then redistribute them. And in the real world, those approximation algorithms tend to work really well versus the theoretical unsolvable problem. So
right.
Okay, so let's go to the audience questions here. Number one question. This is a UML question. We'll do a little bit of both, a little bit of UML, a little bit of Grady's current presentation here. Mario Ruiz, you are the winner of the free mentoring session as part of the Hack Pledge for asking the question that got the most votes with 93 votes. And so you will be able to choose a participating speaker of your choice and do a one-on-one hour with them and ask them any questions you want after this event over. For those of you who don't know what I'm talking about here, this pledge is kind of a movement to help programmers around the world become better programmers, to bridge the gap between good and great developers by having us all mentor each other and help each other. And you can get more information about that at hackpledge.org. So Mario's question here is, how can UML be added to the Agile workflow? Is it possible to include it into a Scrum process. What do you think, Grady?
Absolutely. Get yourself a whiteboard and draw some UML diagrams, and then erase them when you're done. Most of the diagrams I create, I'm going to throw away, and I will use some diagrams, but not many. In fact, bear with me a minute as we do this. I'm going to bring up another presentation that shows some of the diagrams of IBM Watson's architecture. I think that might be interesting to some. Would you all like to see that?
Absolutely.
Here we go. Let me bring this up real fast. So Watson was created with an agile process, very much so. They had a war room, about 20, 30 people would sit in the same room. And these folks, were mad, amazing developers. They absolutely were. The way I tend to use the UML in an agile process is I'll use it as a language to reason about design alternatives. Ultimately, the code is the truth, but it's not the whole truth, because it doesn't really show me some of the rationale of what I've done. It doesn't show me the design patterns that cut across what I'm doing. Bear with me as this comes up here. Let's see if I can bring this up. Yeah, I think this would be fun to look at. Hang on. Looking for a class diagram to look at. Ah, here we go. Ah, all right. Let's go to this diagram. Share. Okay, so here's a diagram that shows, this is a UML diagram that shows the logical view of Watson. So I believe in Philippe Crucian's 4+1 model view, which is a way of looking at different views of a system. And you're looking here at the major logical clusters of classes. One of these you'll see in the green is the type system, which includes a class called question and another one called answer, and then candidate answers and the stuff. So this is actually quite useful in helping somebody who's coming onto the project to say, how does this thing work? Where do I even begin? And how do I start looking at this code to even begin to modify it? There's another view. Let's look at this one. This is the process view, which shows you the pipeline. So the process view tells me the main processes and threads that work within a system. Here is a diagram that shows the, here's a diagram that shows how the system is actually componentized as you're running in the Jeopardy challenge, because you have low latency. This means data gets pushed in memory as opposed to on the disk. This is as opposed to the high throughput development approach, which is you want to get a quite quick turnaround. You want to make code changes and you want to see the impacts very quickly. So from a component view, Watson is a very layered system. It looks like this in UML. And from a physical view, the deployment view, this is how all of its cores look. We threw basically 4,096 machines at it with several thousand cores at the bottom. So these are the UML diagrams that basically describe Watson. So the way I tend to use the UML in an agile process is I use it to reason about, try design trade-offs, and then I hang around with a handful of diagrams, and that is sufficient to let people who come after me begin to get a landscape of what we're doing.
Makes a lot of sense. Well, Grady, if you have a few extra minutes here, I think what we might do is give access to some of our audience members to your Hangout so that they can interact with you directly. So I'm going to go ahead and paste this into chat. Now, not everyone will be able to get into this. It's just first come, first serve. And so it's there's only about 15 or so people that Hangouts can support for video chat.
Okay.
But because we're a little bit low on time here to answer more questions on the air.
Sure.
But Grady, incredible presentation, mind-blowing. I agree with the audience. This needs to be on TV. We need to do whatever we can to support you in that. The Human Experience, please check it out. Grady Booch, thank you so much. Any parting words before we take off here?
I remember that anyone who follows me, an angel gets its wings. So, Grady_Booch.
Great. Thanks, Grady. We'll talk to you soon.
Thank you. Thanks for having me.
Okay.